In this video, we're going to derive the push-forward or Jacobian-vector product rule for scalar function broadcasting. The elementwise application of a scalar function is typically what you see in the activation functions for artificial neural networks. You can think of them as a function that takes as an input a vector x and gets back a vector y, but it does so in that it elementwise applies a scalar function. So it takes the vector x and let it be composed of the entries x1 all the way to xn, and then applies a function sigma to all the elements individually. So sigma on x1, it does sigma on x2, all the way to sigma to xn. And this will be our resulting vector. These will be the entries of the vector y. So this is y1, y2, all the way to yn. In many programming languages, you might see the operation being defined as sigma dot applied to vector x, and this dot induces some sort of a broadcasting. This is something you would see in MATLAB or also in Julia. If you coded that in NumPy, for instance, and defined the function sigma to be a scalar function, there is some auto broadcasting happening, so you wouldn't need the dot sign. So this is also what auto broadcasting would do for you in NumPy and many other libraries in Python like TensorFlow, PyTorch, and so on that build on these array computations. Let us define the dimensionalities. So let x be an n-dimensional vector. Y is also an n-dimensional vector. And as such, the wrapper function f will be a mapping from an n-dimensional space to an n-dimensional space, and the function sigma, our nonlinear activation function, is just a scalar-valued function. So it takes a scalar and returns a scalar. And now we want to define the push-forward or JPP rule because we want to do forward mode automatic differentiation. This is nothing you would typically do with neural networks, but is still an interesting insight and can be used for some other applications. So the task in the push-forward or in forward mode automatic differentiation is to propagate tangent information on the input, so an x dot, which will be another n-dimensional vector, to a tangent on the output, and let's denote that with y dot, which is also an n-dimensional vector. And the rule on how to do that is that we say that the dotted y is given as the Jacobian of our wrapper function, df, with respect to x, multiplied with x dot. So it's kind of a linearization that we do here. And if we write that down a little bit more explicitly, we see that the Jacobian matrix is composed of all the individual derivatives of outputs with respect to inputs. So we have the derivative of f1 with respect to x1. Then we have the derivative of f2 with respect to x1, all the way down to the derivative of fn with respect to x1. Then row-wise, we can go and say this is the f1 with respect to x2, and so on and so forth. And then let's also add that component here. This is df2 with respect to x2. And then on a diagonal, ultimately we will find dfn with respect to xn. And this one is then matrix vector multiplied with the tangent information on the input. So this will be an x1 dot, an x2 dot, all the way to an nx dot, xn dot. Now let's introspect that a little bit more closely. The derivative of f1 with respect to x1. So this is the derivative of the y1 output with respect to the x1 output. Obviously, we will get that if we take the scalar function, perform its derivative, and evaluate it at x1. So this one here will be sigma prime evaluated at x1. Next up, we have the derivative of f1 with respect to x2. So in other words, how does the first output depend on the second input? And if we take a close look at the primal or the forward computation, we see that due to the broadcasting of the function, only the element in the input vector that is at the same slot as the element in the output vector affects the element in the output vector. And as such, the derivative of y2 with respect to x1 will be 0. So this one is 0. And the same holds true for that entry. This will be 0. f2 with respect to x2 will just be sigma prime evaluated at x2. And we could go on and so forth and would find out that there is only diagonal entries in our matrix. So for completion, let's also do that one here. This is sigma prime evaluated at xn. So in other words, what we have is a diagonal Jacobian matrix. A diagonal Jacobian matrix, and we always get a diagonal Jacobian matrix if the interaction of the original vector-valued function f is only element-wise, and that is by definition what our function broadcasting is doing. So it is a diagonal Jacobian matrix because there is no interaction between the dimensions in vector x. So let us note this down once again, that we get the dot output on y as a matrix with the diagonal entries being defined as the derivative of the scalar function evaluated at the corresponding element-wise primal points. So sigma prime of x1, sigma prime of x2, all the way to sigma prime of xn. And in all other parts, it will be 0. And then this one is matrix vector multiplied with the tangent on the input. So let's also write that down differently. We can say this is the diagonal matrix given by the entries of the derivative of the scalar function, the nonlinear activation function, being broadcasted, and I'm here using the dot index again, to the primal vector, or applied to the primal vector, and then this one multiplied with x dot. And whenever we have the matrix vector multiplication of such a construction with another vector, this is identical to an element-wise multiplication. So we could also say that is the same as sigma prime broadcasted on the primal vector x, element-wise multiplied with the tangent on the input x. So let me just note that down. This will be the derivative broadcastedly applied to the primal inputs. And what we see here, that was an element-wise multiplication. So an element-wise, or in other words, in order to forward propagate the tangent information, we scale each entry in the tangent vector with the derivative of the scalar function evaluated at the primal. And as such, we can then define the full push-forward rule. So the full push-forward rule, so we can forward propagate tangents on the application of a broadcasted nonlinear function on the primal inputs x and the tangent inputs x dot to first, we do the primal computation, which was sigma broadcasted to vector x. And then we do the tangent computation, which was sigma prime broadcasted to vector x, element-wise multiplied with the tangents on x. So this one will be the primal output y, and this one will be the propagated tangent. This is the tangent on the output y. So let me make a box around that. Now I want to leave a small remark on some commonly used activation functions in neural networks. So this is the rather general rule for probably any scalar function you could come up with, but typically one only uses a handful of functions, and those have some interesting derivative properties. For example, if we had the sigmoid function, the derivative of the sigmoid function is given as the sigmoid function originally applied to x multiplied with 1 minus the sigmoid of x. And since we already computed the primal computation as the output y, we could reuse that in order to get an estimate on the derivative. Or the hyperbolic tangent, we know that its derivative is 1 minus sigma squared of x. And here we could also reuse the primal computation. So in other words, these nonlinear activation functions have been chosen also in parts because of their favorable derivative properties to reuse a computation from the primal pass. A big thanks to all the patrons of the channel. If you also want to support my vision of free education on these advanced mathematical topics, you will find the link to the Patreon page down in the video description. I hope you enjoyed that video. If you did, then please leave a like and consider subscribing to the channel. There is more awesome content on automatic differentiation rules. Here you will now see similar videos, and I hope to see you in one of the next videos.